So hi everybody. I Before I start, this is going to be an engineering video. And before I start, I just want to mention I have a pet peeve that's shared by one of my favorite rock stars, which is surprising because he's a drummer and a lyricist, and I'm a guitar player. Neil Peart from Rush had a pet peeve about integrity, and I kind of do too. I won't go on about it, but I really kind of liked not only did I like Neil Peart's drumming and what was my favorite band before I played guitar for 2 years, from 13 to 15 years old. But he talked about integrity a lot, and when I say I want to do a video about this and this, I don't mean to not do it if I don't. And that's part of what I call integrity for Shirtless Guy. And I said was going to do an engineering video, and I didn't. That wasn't just, hey, I'll get a bunch of views if I say that. I really want to do it. So here we go. All right. I decided that I'm probably going to do a series of these because it's an interesting topic and it's what I basically started out to do with my life until I was 20. And so let's just start like slow and realize it's not the only video. And let's just learn something rather than just, oh, that's impressive, Jimmie. Thanks for showing off. Um, okay, so let's just take it a little bit at a time and maybe you guys can learn something about engineering. I went to Harvard College. It cost my dad $50,000, 50, to go to Harvard College for 3 years in the 80s. So let's not waste his money any more than we have to, eh? Okay, so for engineering is related to math, and in math there's also, so math is important. In math there's a thing called a function. A function is basically something that if you have an x, this is the x-axis and this is the y-axis. For every x value, there's only one y value. So a circle wouldn't count because that's got multiple y values per x value. But a function could be anything that, just as long as it has one value per every value of x has a unique value of y or no value, but not more than one. A function is aperiodic, means not periodic, if it never repeats itself. But it's periodic, as the word sounds, if the function, whatever it looks like, repeats its cycles. Like it does the same thing over and over again forever, but in both sides of time or whatever. And periodic functions have what's called a period and also a frequency. If this goes over everybody's head, I'm sorry, but if it bores people, I'm sorry also. A frequency is how many cycles per second. If it's in hertz, so I call that F. If it's in hertz, 1 over the period. I'm going to make capital T the fundamental period, which I'm going to talk about in a second. But that's not even 1 over t? Yeah, it is 1 over t. The inverse of the, in other words, the inverse of the period. Okay. If the fundamental period is how long it takes for one cycle, then the frequency is one cycle per period per fundamental period. In other words, if the fundamental period, if a function repeats every 5 seconds, then the period in hertz would be 1/5, because it's one cycle per how long the period is, 5 seconds. Or like 60 cycle hum, or I don't know much about that, but I think they say that if the frequency is 60, then something to do with electricity or something, I don't know. Now the period can be, now if you notice something, if you double the period, it's still also a period. It's just not the fundamental period. If the period is 5 seconds, then 10 seconds is also a period of it, because if it repeats every 5 seconds, it also repeats every 10 seconds, and it even repeats every 15 seconds. Every multiple of the fundamental period is also a period, but the fundamental period is the shortest period that can be called the period of the function. So that means it would have, if it's the shortest period, it would have the highest frequency. So the highest frequency of possible frequencies of a certain function that's periodic is the fundamental frequency. Okay, but I don't want to do hertz right now, because that's not what engineering works with. Engineering works with something that's engineering works with uh, uh, something that involves the math of a circle and periodic motion around a circle. So let's have a circle with, and let's say the radius is 1. Now I'm gonna use angular. I'm gonna use angle. I'm gonna talk about angular frequency. But before I do that, I'm gonna talk about angle. Now, angle is in math is based on is symbolized by theta. I'm not writing this very well. The Greek letter theta is an angle, and the angle we don't use degrees for angles in engineering. We use radians, and a radian is if you have a circle with radius 1, how much arc is transcribed by the angle that is measured off, starting on the x-axis and going counterclockwise. So if I go from here and I go a quarter of a turn, which would be 90 degrees, that would be, well, first of all, the ratio of the diameter to the circumference of a circle is pi. So pi equals d over c. But d is 2 times r because the diameter is twice the radius. So that means that pi equals 2r over over diameter. Wait, sorry, pi isn't d over c. Sorry about that. It's c over d. Circumference divided by diameter. Sorry about that. So, if the diameter is 2, okay, the diameter is the radius. Diameter is twice the radius. So therefore, pi equals c over 2r. Okay, and that means that c. Right, I'm going to change this right up here. C equals 2 pi r. That means the circumference of a circle is 2 pi times the radius. That means, therefore, that means that if I have a radius of 1, a circle of radius 1, the circumference is 2 pi. Because if I go all the way around the circle and back to the start, that is 2 pi. That arc I've measured is 2 pi times the radius, which if the radius is 1 is 2 pi. So therefore, an angle of 360 degrees is going to be called 2 pi, because that's how much arc is measured from a circle with the radius involved. So if 360 degrees equals 2 pi, then 180 degrees would be half of a rotation around the circle would be pi. So an angle of 180 is then pi, and then the angle of 90 would be 2 pi, because pi over 2. Sorry, pi over 2, because that's half of pi. So 90 degrees would be pi over 2. So 90 degree angle is pi over 2, 180 degree angle is pi, 270 degree angle is 3 pi over 2, and 360 degrees angle is 2 pi. So that is for angle. So I know that the first part of a study is often the hardest part, because you have to establish boundaries and context, and it's really hard to do, but we're doing it. So if theta is an angle, and I want to know, and it's measured in radians, so I call it RAD. Omega is the angular frequency. Now, angular frequency would be radians, because that's an angle, per period, or per second, radians per second. And that's how fast the angle is changing in time. And if around a circle, the period is 2 pi, because that's when the angle starts over again. Every 2 pi radians, it comes back to the start. So therefore, the fundamental period okay, yeah. So I got it now. So so every 2 pi, the function starts over. So you could say that so the fundamental frequency would be radians per second. And how long does it take? How long does it take to go around the circle? That the time in which the function takes to go around the circle is called the fundamental. Is called the period, because that's how long it takes for one rotation or one repetition. So, in other words, uh, if it covers 2 pi, one rotation is 2 pi radians, and however long that takes, if it takes 5 seconds to go around the circle, then the frequency in radians per second would be, watch this, 2 pi over the period, because if it takes 2 pi radians to make a rotation, and that's radians per second, however long the rotation takes, that becomes omega, the angular velocity, how fast the angle is changing with respect to time in radians. So if the fundamental period is 5 seconds, let's say the fundamental period is 10 seconds. If it takes 10 seconds to go in the circle, then omega would be 2 pi over 10, which is equal to 5 pi, and so forth. And this little equation, which I'm going to highlight here, omega equals 2 pi over the fundamental period. Now, like I said before, the period, multiples of the fundamental period can also be the period, because if it takes 5 times, if it goes around the circle in 5 seconds, it also goes around the circle in 10 seconds or 15 seconds. So this could be multiples of this. But the one that's the smallest possible period for a function is called the fundamental period. And if this is a fundamental period, then the fundamental frequency of, or just call it the frequency, because any first of all, this, let's call it the frequency for now, is 2 pi over the period, and any dividend of the fundamental frequency is also a frequency. In other words, half omega over 2 would also be a frequency, because that would be if the fundamental period is twice that. So it would be, like if the fundamental frequency is 10 seconds, then if it's 5 seconds, then 10 seconds, it would be, that would make it half, that would be a half of the fundamental frequency. And if it's 15 seconds, it would be a third, and so forth. But basically the fundamental frequency of a function is 2 pi over t. And this little equation, omega equals 2 pi over t, is very important in engineering. It's a very simple one, but to understand the context of it, it takes a little thought. And so I'm actually doing some real math now that we explain that. Omega equals 2 pi over t. I'm going to show an application of that, and something that actually uses some more higher math than I've been showing, because this has all been basic stuff. There's something in engineering, and especially systems, called it's called Euler's theorem. L-E-R-S formula. Actually, I'm going to use Euler's formula. It says that so I want to go this far. I do. E to the I theta equals cosine theta plus I sine theta. Now, what that is, it describes motion around a circle on what's called the complex plane. Now, this is important. Complex plane in engineering is a plane of numbers, but the x coordinate is real numbers. X is real numbers. All the numbers we normally think of as numbers, and the y coordinate is I times y. These are imaginary numbers. An imaginary number is a multiple of pi. I mean, a multiple of I, and I equals square root of -1. And then it would imply that I squared equals -1. And there's no number like that. There's no number that when you square it equals -1, because a negative number squared is still a positive number, so not -1. And a positive number squared is still a positive number, thus not -1. So we just make up a number called I whose square would be -1, even though it doesn't exist. And that would be the I coordinate, the I axis. The I axis is the imaginary axis. So any number that you can plot in 2 dimensions is called a complex number, because a complex number is a number z that's equal to x plus iy. In other words, a complex number is a sum of a real number and an imaginary number. And whatever point you are on the plane, of this plane, would be whatever complex number you're talking about. So that this would be maybe 1 plus, if this were 1, this point would be 1 plus I, the 1 plus 1I, and so forth. Well, I don't mean to erase the IY part. What if I have a circle on the complex plane? That's what I'm going to call it. It's plane because it's 2 dimensions, and complex because it's complex numbers. And I'm going to make the radius 1. And I'm going to say, what if I have a function, the angle starts on the x-axis and goes counterclockwise for the positive direction? And it turns out in math, well, first of all, if I start here and I start going counterclockwise, then the x value is the cosine. And that's because in trigonometry, cosine equals the adjacent side over the hypotenuse. So that would be this side over whatever the 1 over 1, because 1 is the one is the hypotenuse, or in this case the radius, and this is the adjacent side of the angle, and the adjacent side would be then the x value. The sine is the opposite over the hypotenuse, so that would be this value. The one opposite would be the y value. So that would be sine. The y value would be sine of theta, the angle, and the cosine of theta would be the x value. So in this case, what's interesting, I know it might bore some people, but let's just do this anyway. I said I would do this, and I meant it. Okay, that any point on this circle is going to be x plus I y, because it's and the x part is going to be x equals cosine theta for the reason I just said, and y, or iy, equals I times sine theta. I got to put the I in there. The I doesn't come out of nowhere. If y is sine theta, then iy is I sine theta. Okay, so any point along this circle is x. No, is x. First of all, is x plus iy, but that is equal to cosine. Let me write it better. Cosine theta plus I sine theta. Cosine theta plus I sine theta is whatever point you are around this circle in terms of the angle theta that you're referencing, and the angle of theta is measured in radians. And like I just mentioned with that, what radians are. And it just turns out that since cosine theta has a Taylor expansion that has either odd or even coefficients, terms, and the sine of theta has a Taylor expansion that has odd or even, one of the two terms. It turns out that if you plug it in to the Taylor expansion for something called e to the x, in this case, if it was real, the Taylor expansion for e has both odd and even, terms. And since the even ones or odd ones is one of the cosine, and the other odd or even is a sine, it turns out miraculously almost. Let me just erase this so we can do some actual math here. You've seen this diagram, so that's cool. It turns out that e to the I theta. So if you plug in I theta into the Taylor expansion for E, it turns out that that's equal to cosine theta plus, I mean, write I. I haven't written these things in a long time, so sometimes I'm writing them wrong. Plus I sine theta. And that is the most important, to me, formula in systems engineering. It's called Euler's formula. And basically, E is a number that is E is a number that is transcendental and irrational, not just kind of like pi, only not. E is equal to 2.718281828, but that doesn't repeat like that, but that just happens to be what it is at the start. It's an irrational transcendental number, constant. And it's also the base of something called the natural logarithm. It's hard, I don't want to get into this right now, but if E equals the logarithm, natural logarithm, e to the let's see, E logarithm, let me think, logarithm, natural logarithm. E is the base of the natural logarithm. So it turns out that e to the x, the natural logarithm and x and e are inverse operations. If I take e to the x, if I have e to the x, I take the natural logarithm of it, I get x, because the logarithm undoes the e. So logarithm, natural, that's why I put an in there, e to the x equals x, because the logarithm reverses the exponential process. And this definition of natural logarithm of e to the x equals x is the definition of e given one condition. Given that, okay, you're gonna like this. How do I pick e though? How do I know what to make the basis of the base of the natural logarithm? How do I know how to pick that value? There's a harder way to look at it in calculus, but I'm going to break it down to something simple that just happens to be that identifies it. If the derivative d e to the x dx, that means the derivative of e to the x, the derivative of e to the x dx is how fast e is changing, or at any given time. And the speed of something changing can be called the slope, because it's the rise over run, and rise over run is a ratio of how fast things are moving up or down. And if the if a function is changing, or the derivative of it, d dx of the function, is equal to the function itself. So in other words, if a function is changing such that d e to the x dx, it means how fast e dx is changing in time, is equal to itself. In other words, it's changing however fast it is, however fast the value of it is how fast it's changing. It's basically, the function is its own derivative. That defines e, and there's only one value that works like that. Let me show you that in a second. So d e to the x dx equals e to the x. That defines e, and then the logarithm of e to the x equals x. That defines the logarithm, and is an inverse operation of e. And that would also mean, just before I finish, if I go on to that, logarithm of x, if I take the exponent of it, e to the logarithm of x, since logarithm and exponent are inverse functions, e to the log x would just be x also, because the e undoes the logarithm. So if I take e to the logarithm of x, that is just x. The exponential reverses the logarithm. But before I go on to that, I said something about d e to the x. The function, now this is in real time now. This is not Euler's theorem anymore, but I'm going to leave that up there. I'm looking at e to the x. If y is the here, and x is here, and I'm talking about y equals e to the x, e to the x is a function that's equal, that changes as fast as however much is there. So if x equals if x is minus infinity, oh, let's look at it this way. Let me think. If okay, here's how you do it. For x equals negative infinity, if let's start there. If y is how much you are on the y-axis is 0, then it has a slope of 0. And something with a slope of 0 just doesn't change. It's just straight because rise over run is 0 because rise is 0. So rise over run would be 0. So it has no value, but it's also not increasing. But then as y gets more, a little bit more, it starts increasing more because you have more y there. Because remember, the derivative is equal to the function itself in exponential. And as you get more y, and look at the y value, the function starts increasing more and more and more and more. Now, when you get to y equals 1, the function also has a derivative or a slope or a rate of change of 1. And that would mean 45-degree angle. It's hard to say that 45 degrees, but that's what it would be. Because rise over run would be 1. Because 1 in 45 degrees, the rise and run are both the same. So that would be a 45-degree angle, which is also the value of the function at 1. So therefore, the function, the slope of the function, which is the rate of change of the function with time, would also be 1. And then as y gets even higher than that, it keeps going higher and higher and higher. And as y gets to positive infinity, the function starts changing infinitely much, which would be this way, and that would be rise of run is infinity because the rise would be infinite in no time, so that would be an infinite slope. So that's basically what an exponential function looks like. Y equals e to the x looks like a curve like this. You've seen that before if you've studied math. It's a very fast increasing function because it takes off in a hurry, because the more you have, the more it wants to change higher and higher and higher, and that's how you define e. And then the logarithm is defined as the inverse function of that. So let me show you another example of that. If I say y equals e to the x, and I say, this is probably a better way of saying it, and I take y of both sides, you do the same thing to both sides, logarithm of y equals logarithm of e to the x. The logarithm and e to the x cancel out, so logarithm y equals x. Okay, and then if I start with that equation, if logarithm of y equals x, let's take e to both sides. If I go e and log cancel out, so I have y equals e to the x. So you can go back and forth between log y equals x and y equals e to the x. It's the same thing. And then this natural logarithm with the base of e is defined such that this number e is such that the derivative of e is equal to itself, like I just showed on the graph. And that's where e comes from, and that e, it turns out in Euler's theorem, is such that e to the I theta, which is back to the complex thing, is equal to cosine theta plus I sine theta. And that basically means that on the complex plane, now back to the complex plane now. This is x, this is iy. By the circle of radius 1, any value is e to the I theta. So because if the e to the I theta equals cosine theta plus I sine theta, then that any value along here is equal to e to the I theta. So that's if the radius is 1, because I made 1 e to the I theta. If I want to make the radius 2, what would I do to do that? Well, I would just multiply it by 2. So basically, you could call the value of the function is actually r e to the I r Jesus, excuse my language, I theta. If r is 1, then it's just e to the I theta, because the r, anytime 1 times the thing is just itself. But if we make the radius 2, then any point would be 2 e to the I theta. The point is, let's go back. If you guys are following this, remarkable, because this is engineering. This is not easy. If r e to the I theta, if all this formula is true, then r e to the I theta equals r. Dude, I can't write. R cosine theta plus I r sine theta. So the r makes it possible for the radius to be other than 1. If r is 2, then 2 e to the I theta equals 2. Then the function, which is r e to the I theta, is also 2 cosine theta plus I 2 sine theta. And so what this does, I'm almost done here for today. I'm going to go on about this later. This is called the polar form of a function because it's an angle and a radius, and that implies circular coordinates. In other words, a radius and what the angle is. That's called polar coordinates. These are called rectangular coordinates because that's square. R cosine theta, x, is the x thing, and plus I r sine theta is the y thing. So it's a rectangular way of looking at it, x and y, as opposed to radius and angle. But either one works, and this is the interchange between the two. To go from polar coordinates, which is this, to rectangular coordinates, just use this formula. To go from rectangular coordinates to polar coordinates, also use this formula, but that's a formula for that is basically Euler's formula which is good for plotting numbers on the functions that are especially periodic, because if it goes on circles, it's periodic, around the complex plane, which is the plane where x is the real value and y is the imaginary value. And if you can get your head around just what I've said, you could probably and really understand it and get it, which I'm trying to hope you do. But if you don't, you don't. But if you do, you do. You could go to probably Harvey Mudd and at least learn something from a lecture. You might not get it all, probably wouldn't, but you get something out of it because you know the basics. All this formula is very important in engineering. I don't know if I want to go on about it right now, but maybe I do. Let me think if I do want to go on, if it will go over the top too much. I better stop there because this is installments. I said I don't have to cover everything in one lecture. But anyway, love you guys. Peace, rock and roll. Hope you guys enjoyed the lecture and hope you learned something and hope it was interesting. Love you guys. Bye bye.